Welcome, everyone. For today's prep, we're going to start looking at more algebraic methods for how to calculate limits of functions. And the main story here is this is going to come down to, well, two basic limits, which we'll come back to and talk about in a little bit more detail. And then also these special limit laws, which there's a lot here. So we'll discuss this as well. The main goal, though, is ultimately for us to be able to exactly calculate limits like this. So rather than trying to calculate this limit using graphical methods or a table of values, we're going to see that there's kind of more of a direct way to get the exact value and know that it's the exact value for what this limit is. All right, so let's go back. And let's start with our two basic limits. So these are kind of like the bedrock. These are the foundation for everything we're going to build up from there. So the first one here is the limit of a constant function. So this is our function, just some constant c. So as a little example, maybe we have the function f of x equal to 5. So it's equal, just our function always spits out a constant number. All right, so this is the output of our function. And the nice thing about constant functions is, well, they stay constant, so they don't change. So as our input x changes and gets closer to whatever number a is, the output of our function is just going to stay constant. So it's going to stay constant c. So as our input changes, the output of our function just stays constant. All right, so whenever we see a number and we're calculating the limit of just a number, the limit is just going to be the number. All right, so that's our constant function. Now, another special function is called the identity function. Now, this is a special one, and there's only one of them. And it's f of x equal to x. So this is our identity function. So what does this identity function do? Well, what it says is if you take some input number x, this identity function just gives you out x again. So whatever number you plug into it, it spits it out unchanged. So if you take input x, the output is x as well. So when you see the x here, think of that as the input, and then the x over here is the output. So the input and the output are exactly the same. All right, so what does that mean for our limit? Well, as our input x gets closer to the number a, what does the output x do? Well, since the input and the output are exactly the same, if the input is getting closer to the number a, well, then our output has to get closer to the number a. All right, so these are the kind of the two kind of building block limits that we're going to use from time to time. And from these, with the limit laws that we're going to look at, we can kind of build up all these different complex functions that we want to talk about. So let's look at the limit laws. And let's start with the constant multiple law. So let's see what this limit law tells us. So we want to calculate the limit as our input x gets closer to a, and we want to calculate the limit of this whole thing. We have some constant k times some variable stuff. So we want to calculate the limit of this whole thing as x gets closer to a. And what this limit law says is this constant k isn't really going to influence the limit too much. So we can actually bring it out in front of the limit work that we do. And we can focus first on calculating the limit of the variable terms. So when we have a constant k multiplying some variable stuff, well, we can just kind of first calculate the limit of all that variable stuff and then multiply our result by whatever constant that k is. All right, so that's one of our properties. Another way to think of that is if we have a constant, we can kind of bring it out in front of the limit sign. Okay. All right, so let's actually jump down and look at properties 3 through 6 here. Because most of these, well, these are all of our basic arithmetic. So we have addition, subtraction, multiplication, and division. And limits work really nicely with our operations here. So let's suppose we wanted to calculate the limit of some variable term, some function f of x plus some other function g of x. So we wanted to calculate the limit of this whole thing. Well, what we can do is we can first focus on just the first variable piece, calculate the limit of that. Then separately, we can calculate the limit of the second variable piece, get the limit for that, and then we just add the two results together. So a way to kind of think of this is when we're doing the limit and there's addition there in the middle, we can kind of split up the limit process over the addition. And that mindset kind of works for the other algebraic operations. So if we have subtraction, so if we have one variable term minus another, well, we can split it up very similar. Do the limit of the first one, do the limit of the second one, and then the subtraction just kind of stays where it is. Same thing with multiplication. So if we have f of x times g of x, two functions getting multiplied together, and we want to do the limit of that whole thing, well, just do the limit of the first part, do the limit of the second part, and then multiply the results together. And same thing for division. If we have a fraction, so we're dividing, we got some stuff on the top, stuff on the bottom. Well, instead of trying to do the whole thing all at once, we can first calculate the limit of the stuff on the top, then calculate the limit of the stuff on the bottom, and then divide the results. Now, there is one kind of exception to this. So whenever we're dividing, we just have to be careful. We can't divide by 0, so this limit can't be 0. So that's going to be a recurring theme. Spoiler, over the next few topics that we do. Division by 0 presents us with some issues. So this last property here only works if this limit of our denominator doesn't equal 0. If it does equal 0, well then we run into trouble, and we'll see there are ways to handle that, but we'll get to that later. All right, so the last one here is if we have an exponent. So if we have some variable stuff, f of x, and then that whole thing is getting raised to some exponent r, and we want to calculate the limit of that entire thing, well, we can kind of bring this limit sign inside the power function there, and first get the limit of the stuff inside, and then once we have that all figured out, then we can just apply the exponent to the result. All right, so we've got our power rule here, and there are some exceptions to this one as well. So this one, you can't have a negative. You just have to be careful. The result has to make sense. So if this exponent is like the square root, you can't end up with like a negative inside the square root there. So there are some exceptions to this one as well. We'll just say it needs to make sense. So there's different types of exceptions, and they're all very special cases. This special case down here is a little bit more in your face. This one, there's some subtle things, but the main one is you just have to watch out. You can't have like negatives under a square root or something like that. All right, so those are our limit laws. So let's try an example just to see how these things work, and we're gonna do this graphical one. It's kind of fun. So we want to calculate, so we're given the graph of some function f of x, y equal to f of x. And what we're doing in this is we want to calculate the limit as x approaches 2 for some brand new function that in some way uses this f of x function, but it kind of builds on top of it. So what do we have? The function that we're calculating the limit of is 3 times the result of f of x squared plus 5. So we're kind of building this brand new function off of this f of x function here. And what we're going to do is we're going to kind of break this function apart using all those different limit laws until we get down to the fundamental core. So let's give this a try. And when we look at this brand new function, kind of the main operation here, the thing that happens, I guess, last, is the addition. So we're going to break this addition apart in regard to that limit. So our first step here is to calculate the limit as x approaches 2 of 3 times f of x squared plus the limit of 5 as x approaches 2. So what we did there, what property are we using? What limit law are we using? Well, we used the one for addition. So that limit law for addition says if we have some stuff plus some other stuff, and we want to do the limit of that whole thing, well, we can do the limit of the first part and then plus the limit of the second part. So that's precisely what we're doing here. We got the limit of the first part and then plus the limit of that second part. So we've got our sum law, essentially. So that was our sum law. When you do these, you don't necessarily have to write out the name of the law, but okay. So what's next? Well, now we're breaking this thing apart. So now the next one is, well, we have this 3 times f of x squared. So kind of the next part of this function is the thing that happens next is this multiplication by 3. So we got to do something about that. And when we have multiplication by a constant, let's pop back up to our, get motion sickness here, going back and forth. But what we have here is a constant multiple, 3, times some variable stuff. So what we can do is essentially we can take that 3 and just move it out in front of the limit. So we end up with 3 times the limit of f of x squared as x approaches 2 plus, now we could calculate this limit, but we'll hold off on doing all the limits till the very end. So we'll save that for the end there. Okay, so we used our constant multiple rule. So I took the 3 and we just moved it out in front. Okay, so what's next? Like I said, we could do this one. We'll come back to that. So we're kind of focusing on the first one. We've kind of gone as far as we can with that second one. All right, so what's going on with this next one? Well, now the next thing is we've got this power function, this squared function. So we got to break our way through that. And we have a nice limit of a power rule here that says when we have some stuff, some variable stuff, inside of a power function, essentially we can take that limit and focus in on the stuff inside of that power function. So we can essentially bring the limit right on through. So what that looks like, and let me see here. There we go. Get out of the way. All right, so let's bring the limit through that squared function. So we have our 3 out in front. Then we've got our, nope. We got to have our squared function, and then we're bringing the limit into that, inside of the squared function. So notice the slight difference. So here, in the previous step, I'm doing the limit of this entire thing. So I have my f of x getting squared. In this step, I'm first doing the limit of f of x, and then whatever value I get from that, I'm squaring the result. And what that power function rule says is that these two things are the same. And then we have our limit of constant 5. Okay, and this was our power rule. All right, so now we've gone really as far as we can go with these limit laws. So there's no more algebraic operations that we can unwind. Limit of 5, there's no algebra, there's no operations there. And then limit of f of x, we don't have any more information about what the formula for f of x is. So that's as far as we can go with this. So now we're ready to use that graph. And we're going to calculate the limit of f of x graphically. So x is approaching 2. We're looking at just the function f of x now. So we've kind of drilled our way through all of that extra stuff. And all right, so let's figure this out graphically. X is approaching 2. So we find 2 along the x-axis. And we do need to think about left and right-hand limits. So if we look at the left-hand side, looks like we're approaching that point which has y-coordinate -2. And if we look at the right-hand side, move along the curve, it looks like we're approaching that exact same point. So this point, the y-coordinate is -2. So the left and the right-hand limits look like they're going to the same place. So we know that the limit of f of x, just f of x, as x approaches 2, is -2 here. So what we can do is take this result and just plug it in. So what we end up with is 3 times -2 squared. So all I'm doing is I'm taking this limit that we just calculated, this number we just calculated, and I'm just filling it in. And that's where I'm getting the -2 there. Now, what about the limit of 5? Well, this is one of our basic limits. So, I didn't even plan that. Didn't even plan that. But this is a constant function. So when we do the limit of a constant function, it just stays constant, so it doesn't change. So the limit of 5 is just going to be 5. So this limit there is 5. And we're done. And if we wanted to, we could clean this up. And what do we get? -2 squared is +4. So we end up with 3 times 4, which is 12, plus 5 is 17. Nice. So this is the idea with these limit laws. We kind of use them to break our function apart as far as we can go until we get down to just constants and some other info. So maybe it's some function f of x like this, or more realistically, it's going to be constant functions and the identity function. We're going to get it all the way down to there. All right, so we'll see more of this in class. So give the preparation problem a try, and we'll see you in class. Bye-bye.